Okay, the last problem, the last example that we are going to solve in this chapter 14 is this example 1412. So what we have is, we have two teapots. One is made of ceramic, and the emissivity of this teapot is 0.7, and I'm going to write this here. So this is the one made of ceramic. The other teapot is a shiny one, and the emissivity is 0.1. So this is the shiny one. The emissivity for this one is 0.1. So the ceramic is going to be a good emitter. The shiny one is not a good emitter. Each one holds 0.75 liters of tea, so 0.75 liters of water. In other words, the mass is 0.75 kilogram, 0.75 kilogram of water. At this temperature, this initial temperature of 95 degrees. Okay, so this is the temperature of the pot. Consider that the area of the teapot, okay, so the area of the teapot is 0.05 square meter, okay. Both teapots are equal, so I'm just going to rewrite the same thing for this other one also, the shiny and the ceramic. What else do they tell us? We want to estimate the rate of heat loss due to radiation from each one. There is one more thing that we have to read. If you read the whole problem, we are going to compare the heat loss due to radiation, assuming that the surrounding is at this temperature of 20 degrees. Okay, so this temperature of the teapot is our T1 in that equation that we have for the net flow, and T2 is the temperature of the surrounding, which is this 20 degrees. So let me put also here this 20 degrees. Okay, so part A is that to estimate the temperature. Part A is that to obtain the rate of heat loss. So let's do first part A, and then we'll read part B. So part A, we have to go back to that equation that we talked about, the net flow. So to compute, to find part A, we are going to use this equation. So the question of the problem is this, okay, the rate, delta Q divided by delta T, which is equal to E, the emissivity. We have the emissivity of each teapot, sigma, which is the Stefan Boltzmann constant we have there. So 5.67 multiplied by 10 to minus 8 watts per meter square, and Kelvin to the fourth. Don't forget this is Kelvin. The area we have, it's the same for both, so it's 0.05. And then we have to put the temperatures. So T1 to the fourth and T2 to the fourth. So T1 is the temperature of the source, the object that is emitting, and T2 is the temperature of the surrounding. And so the object is emitting, but it's also absorbing from its surroundings, so minus what it absorbs from the surrounding. So this is the equation that we have to deal with to find this rate of heat loss. The only thing that you have to be very careful is with this temperature. Remember, we are not going to enter the temperature in Celsius. We are going to enter the temperature in Kelvin. So what does that mean? Instead of 95 degrees, we are going to put 95 degrees plus 273. So the T1 is equal to 368 Kelvin. So that's what we are going to enter for T1. For T2, it's going to be 20 Celsius plus 273, so 293 Kelvin. So that's what you have to enter here. Okay, so careful with that. If you enter these numbers properly, in Kelvin, and put each one of these temperatures to the fourth, compute that, you will find that for the ceramic pot, the rate for the ceramic pot is close. It's not exactly this value, okay, but it's close to 20 watts. Joule per second, watts. For the shiny one, is less because the emissivity is smaller, so it's not a good emitter. It's 3 watts. Again, this is approximate. This is not the exact value. It's close to this value. Okay, so this is part A. Let's see now what is part B of this problem. Part B is very interesting. The question is estimate the temperature drop because of this emission. These teapots, they are losing more energy than they are absorbing. So because of this loss of energy by radiation, the temperature will drop. And we want to know what is this temperature drop? What is the delta T? Okay, by how much the temperature will drop after 30 minutes for each teapot. Okay, so again, we are going to separate things. The ceramic and the shiny one. Okay, we already got the rate. No? We already got the rate loss due to radiation. For the ceramic, this rate, I'll call it this delta Q over delta T, was 20, okay, 20 watts. For the shiny one, this delta Q over delta T was approximately 3 watts. Okay, let me write this a little better, 20 watts. We want to know the temperature drop. Well, let's have a look at the equations before we do anything. So we have delta Q over delta T. So this is the amount of energy that the pot is losing per time. What is Q? We learned this in this chapter 14. Q is given by mc delta T. This is what we are after. Okay, the question B is what is this delta T? What is this change in temperature, this drop in temperature caused by the loss of energy through radiation? Okay, so Q is given by that. And at the bottom, I have delta T. Okay, this is the equation that I need. I want to obtain this delta T. The left side I already have is either 20 for this pot or 3 for that pot. So let me start with the ceramic one. Okay, so for the ceramic one, on the left side, I have this 20 watts. On the right side, what do I have? The mass. The mass of what? Well, let's think that the mass of the pot itself is negligible. What we count is just the mass of the water inside, of the tea inside, which we already said is 0.75 kilograms. So that's what I'm going to put here for the mass, 0.75 kilograms. What is C? C is the specific heat of water, which we know is 4186. And then delta big T, which is the drop in temperature. How about the bottom? The bottom is time. Which time? 30 minutes. 30 minutes in seconds. So we have to put here 30 minutes multiplied by 60. And that's it. No? We will then obtain the temperature drop for the ceramic pot. For the other one, the shiny pot, is the same story. But the difference is that on the left side, the rate loss is 3. On the right side, everything is the same. 0.75 for the mass, 4186 for the specific heat. Delta T is our unknown. And for how long? What is the time? 30 minutes. 30 minutes, then multiply by 60. We are using international system here. Okay, so these are the equations that you have to solve to find the solution. So the temperature drop for the ceramic is 12 Celsius. Okay, when we are using the equation Q equals to mc delta T, this is in Celsius, the C is in Celsius, so that's why we get this drop in Celsius. And for the shiny one, you will see that we get just 2 Celsius. No, it doesn't emit much, so it doesn't lose much energy. Okay, so these are the values. Again, these values are approximately, they are not exactly those ones, but they are very close to that. But it would be good for you to double check.